Welcome back. I'm Dave, and today we're going to look at Voronoi diagrams. So this is named after a famous Russian mathematician called Georgy Voronoi, and it is part of the IB syllabus, AI specifically, so applications and interpretations. It does not appear in the AA course. Voronoi diagrams are made up of basically cells, and in those cells are sites. So I'm going to go through in this first part of the video what the terminology is: sites, edges, cells, perpendicular bisectors, what equidistance means, and additional sites. Then we're going to look at some exam style questions. So let's get straight into it.
It's a bold strategy, Cotton. Let's see if it pays off for him.
Okay, before we start then, we are going to need to use some formulae. These are in the formula booklet for standard level, also higher level. The first one being the gradient of a line. So if we had 2 points, we can certainly find the gradient between those 2 points by simply finding change in y over change in x. So rise over run. For distance between 2 points, it's basically essentially Pythagoras. So we are going to be looking at the distance between, let's call this A and B. It's a change in the x direction squared, sum it to the change in y direction squared, and then square root. It is Pythagoras. If you have unpacked the formula, you'll see. The third formula that we're going to look at is the coordinates of a midpoint. So therefore, then we just simply add the two coordinates together, as in like we add the x components. So we'll call it x1, y1, and then we'll have x2, y2. And we simply add the x components together, divide by 2, and then the same for y, divide by 2, and we will find what's called the midpoint of the two coordinates. The gradients formula is not in this gradient, this perpendicular gradient is not in the formula booklet. So we just need to sort of maybe provide a very, very quick understanding of this. Let's say I had a line, and this line had a gradient of 2. Now this little formula that I've written here says that when you multiply two perpendicular gradients together, so imagine I had another gradient like this pink one. When I multiply the yellow gradient by the pink gradient, I should end up with -1. So I'm just going to label this as like M2. So my formula states that M1 times M2 should equal -1. If M1 was 2, M2 is yet to be found, equals -1, then I can simply divide both sides by 2, giving me -half. Now, if that was too complicated for some, you might just want to remember it as the negative reciprocal of the first gradient. So here we go again. Let's say I had a gradient of -half, for example. Okay, so look at the green line here, -half. And now I want to know what the gradient is passing through here, the perpendicular line represented in purple here. So therefore, the negative reciprocal of -half. So it will become +2. So therefore, we can see then if we were to multiply these two values together, we would get 2 times -half, and that would result in -1, which is correct because I just stated over to the left here that the two gradients multiplied together should equal -1. Right, there's a quick rundown on the formulae that we're going to use in Voronoi diagrams. Let's move down to the next section.
Do it. Do it.
Okay, so on this section here, we're going to look at sites, gradients, and perpendicular bisectors. We're just going to take two simple locations and try and find a perpendicular bisector between them. So I've just got a map on the left here with Philadelphia and New York. I just want you to pretend as though we have put a pin in a map and we have put those coordinates or those values over onto a Cartesian grid like this. So you'll be given this in an exam, two certain sites, okay, will be listed. Now, there may be more than two, could be 3, could be 4, could be more, but this is the beginning of how we would construct a Voronoi diagram. First things first, we would need to find the midpoint of the two sites. So one of our formula were to find the midpoint, we would need to sum the x values together and divide by 2. So I can see that 8 plus 2 is 10, divided by 2 is 5, and 9 plus 3 is 12, divided by 2 is 5, 6. So the midpoint of P and N is actually 5, 6. So let's go ahead and mark that on. So we've got 5 and 6. Let's use a nice bright color here. There. Okay, so that's a midpoint. Now, you can find that just by counting the squares and sort of doing it visually. That's absolutely fine if the squares are there. Now, the perpendicular bisector will run through sort of like here. Okay, now again, the gradient a lot of the times be done by sight, but I'm going to just show you how you would do it because there may not be a diagram. There may just be a blank piece of paper, or it's not to scale, or we don't know. So we're going to use the formulae to find that perpendicular bisector. So step one is to find the gradient between the two sides. So that's NP. So the grad of NP. Well, that's changing y over changing x. So that's y2 minus y1. So that'd be 9 minus 3, okay, which is simply 6, over x2 minus x1, which would be 8 minus 2, which is also 6. So we have a gradient of 1. Now that's nice, because therefore then what we can do is we can find the perpendicular gradient, so perp grad, right? And the perp grad, remember, above was listed by finding the product of the two gradients must equal -1. So therefore then m1, which is this value 1, this is, I'll call this m1, times m2 must equal -1. So if one of the gradients is already 1 given, we can just rearrange to make m2 the subject by dividing both sides by 1, and we get -1. Now that's quite easy. It's a nice number, so the gradient is -1. We go over to the side here. When the gradient is -1, it means that for every x value that we move across 1 unit, we go down 1 unit. So therefore, if we start here at the center of the x, we go across 1 and we go down 1, okay? And then we do that again, go across 1, down 1, and we can start to see a pattern emerging here, okay, that this nice line that's going to be formed. And that would be my perpendicular line to Pn, okay? So I don't need this working out. You can get rid of this here. But what does that mean? Well, if it gets more complicated, it's going to section the graph up into more sections. But right now, what we've got in front of us is we have some cells. We have cell P, which is all the points that are closest to site P. And then we sort of have cell N, which is all the points closest to site N. Now, if you are standing on that line, if you are somewhere here, let's say, for example, you are equidistant from P and to N. So that word equidistant is because you are the same distance away from both the sites. Okay, so we've covered a few things there, gradients, perpendicular lines, equidistance, and I've shown you how we can calculate the perpendicular gradient if needs be. Section 2 now. What does a completed Voronoi diagram look like? Well, if you could just imagine that what we did here is we had, let's say E and C were the 2 points above. So there's Philadelphia and New York. What we did is we just found a line bisecting those two sort of sites in half, creating these two cells. Now, what happens if we had multiple sites? So we had site A now. Well, we would have to do the same for A versus E and A versus C, and on this diagram, A versus B. So what we will do is we get more intersections, we get more perpendicular bisectors, and it starts to create this lovely shape, this kind of mosaic shape of the graph that we're looking at. It splits it up into different sections. So those are very specific to Voronoi. So these are called the edges that we create. These are the cells, the area inside, and then we just talked briefly about the sites. So we have sites, edges, cells, and where two or more edges meet, that would form a vertex. Okay, so we're going to work through one of these basic exam style questions on Voronoi diagrams. The map shows 3 hospitals, that would be A, B, and C on the left-hand side. When there's an emergency, the nearest hospital is alerted. Which site is closest to 6-3 here? So that would be site C. I can just see that visually. 4-6. 4-6 is here, so I can also see that that is site A, just visually. If we needed to find distance, we could just use the distance formula, but it doesn't ask us to do that. So we've done A. Construct cell B, the region of the city closest to hospital B, and label the equations of the edges. Okay, so I'm going to move over to my pencil here, and I'm going to try and find the bisector of AB. So the bisector between A and B would pass through the midpoint, and I can visually see that the midpoint is here. It is the perpendicular bisector will be a horizontal line that passes through that. And the reason why I know that is because I can see that AB is a vertical line. So the horizontal line will pass through the midpoint, and it will have an equation of y is equal to 4. It asks us in the question to do that. It says the equations of the edges. The other bisector through B and C would go through this point here that I've just put across, and therefore then the edge would pass through that point going through like that. And again, the equation of that line would be x equal to 4, which is a vertical line passing through x on the x-axis. I'm going to erase this and this because in a moment we're going to draw a bisector for AC, and those parts of the construction lines are actually no longer needed. When they meet a vertex, something will happen at that vertex, like they will veer off in a different direction, and I just want to get rid of that construction line right now because it's not really relevant. It says, where is cell B? Well, cell B is down here. I've found cell B, and that's what they want to see. So I'm just going to write down that this is cell B, and I have answered part B of the question. Complete the Voronoi diagram now for all the city's hospitals, okay, clearly labeling the cells. So what I'll do is I want to find the midpoint of AC. We can find using the midpoint formula or just count the squares. So I can see that site A is at 1, 6, and site C is at 6, 7, 2. Okay, now the midpoint formula is sum the x values together and divide by 2, and then sum the y values together and divide by 2. So doing that, we would get 4, 4. Okay, so the midpoint's at 4, 4. But like I said, you could have just really sort of counted the squares, to be honest, and just found it like I did the other one. But that's your choice, right? And therefore, we now need the perpendicular gradient passing through that orange cross. Now, what's best is if I find the gradient of AC first and then convert that gradient into a perpendicular gradient. So if I just go grad AC, then it's the gradient between A and C first. So let's do that now. So that's y2 minus y1 over x2 minus x1. So y2 would be 2, subtract 6 over 7, subtract 1. So that would result in minus 4 over 6, which would be minus 2 over 3. So going up to this point here, if I wanted to draw that gradient, I could, but it's actually not necessary because I'm just going to immediately find the perpendicular bisector to this, which is the negative reciprocal. So the negative reciprocal of that would be positive, and it would be 3 over 2. So my second gradient, my perpendicular gradient, is 3 over 2. So that's quite important because we need to know that this is the x and then this is the y. So it means that as I go across 2, I go up 3. So I increase by 3. So I move across 2, then increase by 3. So if I was drawing that on here, then what I would do is I would start from the midpoint. So as I move across 2, I go up 3. So let's go 1, 2, then 1, 2, 3. And we can go backwards and sort of reverse and also get that. But to be honest with you, I've already got 2 points, and 2's just enough that you can draw a straight line through those points. So I'll draw a straight line through those points there. And we can see that now we have our last and final edge. Okay, so this would now leave the following. Okay, this would be cell A, and then this would be cell C. Part D, if you think about this, if you are anywhere on these lines, you are equidistant to that corresponding site. So if I was here, I'm at corresponding site is C and A. So I'm equidistant to C and A. So where are we going to be where we're like equidistant from all the sites, not closest to one than the other? Well, that would be where the vertex is here. So if you place the new hospital here, your equidistance from A to B and to C, to C. So therefore, then you are you've maximized your distance anywhere off that vertex. Then I'm closer to A than I am to the others. So that's not quite right because it's got to be equal distance from all the other sites. So that would be at coordinate 4, 4. Okay, so everything seems to be happening at that 4, 4. 4, 4 is where I'd propose the new hospital. Okay, so we are going to go through an IB exam question. This one featured in May 2023. It was standard level AI, and you will need a calculator later on, possibly for NSolve or simultaneous equations. So let's have a look. So Annie owns 4 cafes represented by A, B, C, and D. Annie wants to divide the area into delivery regions. So that's basically the cells that we've been working on. This process has been started in the following incomplete Voronoi diagram, where 1 unit represents 1 kilometer. The midpoint of CD is 5.5, 1.5. So there's 5.5 and 1.5 is here. So the midpoint of CD is there. Show that the equation of the perpendicular bisector is negative 3x plus 18. Right, it's worth 3 marks. I would say that you shouldn't be using this at all. You have got to derive that. Okay, you have to get to that. If you start substituting values into that, what you're doing is you're essentially using that value, which is saying that you're supposed to show that value. So you're supposed to get to that value. Now, what I would do is I would say that the grad of D to C, okay, is one of the first places to start. Now, somebody might say that you could just visually see the grad from here. I think that is true. Yeah, you can see that the grad is 1 across, 2, 3, so 3 units across and 1 up. So therefore, this is a gradient of rise over run, which is 1 over 3. So the grad of that is rise over run, which is 1 over 3. Now, you could use the coordinates given in the question, but that would just be time consuming. So we have found the gradient of D to C. So therefore, then, the gradient of perpendicular DC would be the negative reciprocal of this, which would be just -3. So that's where this -3 comes from in the result. So now we have y is equal to mx plus c, and we have just found that the gradient of the perpendicular must be -3x, so this will get you points. And we also know that one of the points that it passes through is the midpoint, which is 5.5, 1.5. Going to go over to here now and use the midpoint. So when x is 5.5, y is 1.5. So 1.5 equals -3 times 5.5 plus c. You may need a calculator here for some of you, but 5 times 3 is 15, times 3 again is 16.5, so -16.5 plus c. Add 16.5 to both sides, yielding 18. So then we get our final result here now, that if c is 18, then we substitute that back into there, getting the result in the question. So complete the Voronoi diagram. So basically saying that we have found something CD now that's going to be very relevant to this, and that will be one of the edges. But we can also see that there is another edge that is missing. If you can spot it, it is AD. Okay, there is no perpendicular bisector between A and D. So what I'll do now is we'll just go over to this and we'll look at AD, and we can see that there must be a midpoint of AD. So AD would be in the middle of here. We can see that this has coordinate 1, 1, and this has coordinate 4, 1. So we can say that the midpoint is 2.5, 1. So therefore then we will have a perpendicular bisector that simply goes through that point. And this is what happens. This is why the edge sort of has a kink in it, like a point, because there was something happens there at that point. And it's actually another edge joining. So we always see that. So when we see the deviation of one of the edges, it's usually because another edge is intersected at some point. Okay, and now, so it all looks pretty good to me. I'd say that was completed. That was worth 1 mark, so that was a very straightforward. We didn't have to give the equation of that line either. Okay, so let's move on to the last part. Annie opens an office equidistant from the 3 cafes B, C, and D. The equation of the perpendicular bisector is given by the following. So 3y equals 2x minus 1.5. So just go over to label that on there, that they've given us the equation of this line is 3y is equal to 2x minus 1.5. Now, don't forget, in one of the other parts of the question, what we did is we'd actually calculated CD. Okay, that was one of the first parts. So this is CD, which is y is equal to minus 3x plus 18. So we've been given the equation of BC. Now we want to know where those lines intersect. So we can use simultaneous equations and solve it that way. Probably one of the easiest ways is to use simultaneous equation solver on our calculator, as we have that facility. So I'm just going to jump over to the calculator now, and let's have a look. Menu, algebra, solve a system of linear equations. We've got 2 equations with 2 unknowns, and we're going to just type them in the following way. So we've got 3y equals 2x minus 1.5. Go down, and then the other one was y equals minus 3x plus 18. Press enter, and we get the coordinates being 5.045, so 5.05. That is the coordinate of the intersection point between BC and CD there. Okay, so we go down there and we just simply write that down. And that is how we do the final part of that question. Okay, so in this final part, there is a situation where we will need to add a site. Now, this happens quite a lot. When you add a site, it'll affect the edges of the already existing Voronoi diagram. So if we have a quick look at this now, we have zone A, zone B, and zone C, also known as cell A, cell B, and cell C. And when we add D, that's going to affect some of those edges, not all of the edges. So we can see immediately here that there is no perpendicular bisector for DC. Now, because the numbers are rather nice, I can just visually see that that is the midpoint of DC. Now, also, I can see that the perpendicular gradient of this would be the following, okay? Now, how would you know that if you can't see it? Well, go ahead and have a look at the gradient between D and the midpoint. So as I moved across 2, I went down 1. So rise over run would be -1 over 2, because as you move across, you go down 1, so as you go across. So this was, remember, the y value, and then this is the x value. So therefore, then the negative reciprocal of that value would just be 2, okay? Because when you times them together, you get -1. So this is how I could just sort of visually see straight away what the gradient of this was. So if I go over to the diagram here, if I start here, I go across 1, that means I must go up 2. And that should be this consistent. As I go across 1, I go up 2. So that is one way you can do it, or you can just use the formula, or you could even just use the coordinates and go through that whole process. It depends how much time you've got. Now, I said earlier that there will be a definite point of interest when the edges meet. So I'm just going to put a red dot there. There'll be something that happens here, and it's going to be related to DA. Right. So let's just get rid of those triangles. We don't want too many things cluttering the diagram. So what is the perpendicular bisector to AD? Now, I'm going to use that same principle again. If that red dot is the center, let's just figure out the gradient getting to that center. So as we move from D, 1, 2, 3 across, we go up 1. So the first gradient would just be, okay, we go along 3, we go up 1. So rise over run. So it's just 1/3. Therefore, then the perpendicular gradient to that would be the negative reciprocal, which would be -3. Okay, so if I want to draw the perpendicular gradient passing through AD, I need to have a gradient of -3. So how does that look? Well, it means that for every 1 unit you go to the right, you go down 3. So we go 1 unit to the right, and then we go down 1, 2, 3. Okay, and then we can also sort of do it in reverse. So as we, if we're looking at this coordinate here, we can go to the left 1 and then up 3, left 1 and 1, 2, 3. There's different ways you can do that. Okay, but what I want you to pay close attention to is where I draw this line going through. Now, this is when you do more practice on these, you get a little bit more skilled. But I want to just show you that this part that I'm sort of highlighting here, you don't want to draw this part, because this is cell C. So anywhere in here is closest to C. So this part of the Voronoi edge is just confusing matters. What changed was this edge here that was originally existing has now changed. It's moved to here, because this edge was originally separating cell C and A, right? But now this is not relevant. So I just want to go over this one more time, that the new edges will be this green line. It will be this purple line here. It will be this line in here. And these are unaffected, because the further you move away from D, the less those edges are affected. They're really just affecting the neighboring sites. So those green lines there are the completed Voronoi edges, and therefore the completed Voronoi diagram. Good luck.
Don't forget to like and subscribe to the channel to see more math tutorials. Check out my playlists on my channel or click one of the videos above. I'll see you next time.